All right, welcome to the coding session for gradient boosting. And we will use the same data sets that we use for the other algorithms. So this makes it a bit easier and we don't have to do the whole processing step. So the first one is the Pima Indians data set that we used for k nearest neighbors. So we took a copy and now we open the file. And let's see what we can reuse of this block of code. So the first thing I always do is I run all to see if the Google Drive has been connected. It looks that it's been connected, and we go all the way down. And here I'm just gonna take a look at the results here. Accuracy is about 77.9, which is quite good. It's the best classifier for this data set up to this point. So let's see what we can recover from all this. So this is sklearn. So first thing I'm gonna do is gradient boosting machines Pima Indians. I change the title, and then we're gonna go down and see. Okay, the split here, nothing changes. Xtrain. Okay, here is scaling. Yeah, as we're dealing with decision trees, there's actually no need to scale. Yeah? So we can comment all these lines out. Yeah. So Xtrain, we're gonna delete k nearest neighbors. So here we're gonna change this to gradient boosting machine algorithm, and all of this we can delete. And this is all k nearest neighbors. Here we go. Okay, so we're gonna start building the code from here. All right, so the first thing that we're gonna do is we're gonna install the Bayesian optimization library. This is the library that we will use in order to estimate our parameters, to do the parameter tuning. So let's run that code, and it will install this Bayesian optimization library. Done. So after this, we're gonna import all the necessary libraries. First XGBoost, that's XGB, and then we're gonna import the classifier because we will use XGboosting as a classifier. We will do a binary classifier, and then we import the Bayesian optimization software, and sklearn. From there we're gonna import cross-validation score. It's something that we used in the past as well. All right, let's now start with the tuning of our parameters. So tuning parameters, let's say actually hyperparameters. Yeah. And we're gonna use the following block of code for that. This is the block, so we're gonna create a dictionary that gives your parameter as well as the range in which to be searched. Yeah, and then we're gonna create a model, call it model tune, which is the XG classifier. njobs equals -1 means that you will use all CPUs if you have more than one. And then basically what we're gonna do is we're gonna look at the cross-validation score here with the model tune. And the cross-validation will be 5-fold cross-validation that we have also discussed in the preparation video for this code session. And as scoring metric, we will use accuracy. And these two little blocks here, they will actually initiate the Bayesian optimization process. Here you see that we will start with two initial points, and then we're gonna do 5 iterations, and then we will print the max values. So here we go. You see, it takes a little bit of time. All right, we're done. So now we're gonna create a model, and using the parameters that we've looked for to optimize. Call sample by tree is 0.7. Learning rate is 2.16. So let me put 2.16 here. Gamma is 0. Maximum depth is 10. Yeah. Minimum child weight is 3.78. So let's make that a 4. And we have 115 trees or rounds. Yeah, so we change this to 115, and then subsample is roughly 0.6. So let's fit the model, and then calculate what the accuracy would be with our traditional 3 lines of code. So let's run this, and here we go. Accuracy is 74.6%. Is this a good accuracy? Not really. With k-nearest neighbors, we had 77.9. So it's not excellent. Yeah. So the next thing that we need to do is take a look at the confusion matrix. So let's enter the code for the confusion matrix, and let's run it. And this is the result. You see, it's not really a great classifier because you have 19 false positives and 20 false negatives. Yeah, it's something that is not really acceptable in terms of a result.